Okay, hi y'all. I'm wondering if you can hear me. Like you can. Okay, here we go. So I got an email last night from someone asking me to go over something. So I'm going to pull that up and I'll do that first. Okay, so it looks like it was a nomenclature question and it was from one of the final exam. The practice final exam. So I'm going to draw it out for you. It just asks to give the IU pack name for this. So here we go. And there's a possibility that these aren't all right. Part of why, so I basically did this practice final exam. My coworker made it, and we pulled a bunch of questions from the test bank, and then we didn't check the answers. I just immediately worked them, so students would get an authentic experience of what it was like for me to actually go through and work the practice problems for them to actually see. So if there was a mistake, I didn't catch it until the video. So I might have addressed it in the video or I might not have. Honestly, I don't remember. Um, but I'll just go ahead and work this again. 1, 2, 3, 4, 5, 6, 7. So I count 7 and 1, 2, 3, 4, 5, 6, 7. This student who sent it to me said they couldn't find the right answer, and that's probably because these are all 6 or 5. So I actually agree. I think this is not hex, but heptane. And then we have 2 ine and 4 ene. And the reason I started numbering from this side is because double and triple bonds have higher priority. Really, double bonds have higher priority than triple bonds, but both of these have higher priority than methyl. So if you started from this side, 1, 2, 3, this would be 3 ene, but starting from this side, it's 2 ene. So I think they're close enough. Hi, oh, it's nice to see y'all. I think it's close enough that I would probably start numbering from this side. That's my thought. So, and then it's also 6-methyl. So if I was naming this, I would say 6-methyl hept 4-ene 2-ine. If you numbered it from the other side, let me just do it just to check. 1, 2, 3, 4, 5, 6, 7. Yeah, I think even though 2, 3, 5 is lower overall, but I think if the option between 2-methyl and 2-ine, everything else being equal, you would make 2-ine be smaller. So I think this would be the right answer. So I agree with the student who sent me that. I don't think that there is a right answer here. So sorry for any confusion. Okay, it looks like there's a few people here. Do y'all have any questions for me to go over before the final today, or any things you want me to look at? Oh, this person actually sent me another one. I just realized. It is 3-methyl-2-pentene with mercuric acetate and THF ethanol. Okay, so this question, it's written out 3-methyl-2-pentene. So I'll start with that. 1, 2, 3, 4, 5. 3-methyl, it's 2-pentene. 1, 2-methyl. Nope, 3-methyl. 1, 2, 3-methyl 2-pentene. There we go. Is treated with HGO. It's actually O2 CCH3 2, but it would act the same in THF and ethanol. And then it does the reduction. Okay, so the first thing I think is this basically would act exactly like the oxymercuration demercuration. It's a slightly different thing that's happening on the mercury, but it's still going to have the O2 CH3, and one of those bonds is going to break. Go back to that arrow down there. And then it'll do the bridged ion, and then your ethanol will be what attacks. So it will attack here, and this will break. So this is O, and it would have the ethanol with the H plus and HGO2CCH3. This would be anti-formation initially. So this one would be a wedge and one would be a dash, but on the step where it gets the mercury gets reduced to a hydrogen, it scrambles the stereochemistry. So you would basically just be able to say there's this plus and an enantiomer. So that would be the answer to that question. So you don't have to know how to name ethanol at this, or ethoxy at this point. There's one question on the final, but you can answer it if you just are able to know E and Z. You don't need to know how to name the ether yet. So as long as you can draw that structure, that's good enough. Okay, Alexandra asked what NMR is. NMR is nuclear magnetic resonance imaging, and it actually is the same technology as MRI, but we just use it to look at the hydrogens that are present. I didn't include that as a main idea on your final. It only is a bonus question on your final, but if you want to learn about it, we didn't do it in class, but I do have a YouTube video where I went over it. The only thing is there's one bonus question on it, so you don't have to worry too much about that. So I won't spend a ton of time going over it. It basically is just a way that we can look at the hydrogens in the structure and kind of know what's going on. William, I think that's William, asked the main confusion about oxidative cleavage, what we need to know, and if there's a mechanism that we should know. You don't need to know the mechanism for oxidative cleavage. So there's two main types of oxidative cleavage. So if you have a double bond and you add it to O3 or, so O3, it will cleave this double bond. And literally, it just adds an oxygen here and here. So the double bond stays intact, but instead of being bonded to the other carbon, it's bonded to an oxygen now. Oh. And so the R groups stay exactly the same. So you can see this has a methyl right here. So the methyl is still there on this ketone. And then over here, there's a carbon chain that's 1, 2, 3, 4, 1, 2, 3, 4. So that stays the same. You have an ethyl on one side here and a methyl on one side there. So you just need to know that for O3. If there's a hydrogen somewhere, so if your double bond looks like this, you can use O3 again to cleave that, and it'll do the same thing. So on this side, you'll get the ketone that looks like this, and over here, you'll get an aldehyde. But if you were to react this same thing with hot KMNO4, it will actually also cleave. But when it cleaves, it is a really good oxidizing agent. You don't need to really worry about this, I guess, at this stage, but you will need to know later that it keeps going and oxidizes this aldehyde into a hydrogen, or a carboxylic acid. So if you want to transform something from an aldehyde or from a double bond, and you want an aldehyde, you need to use O3. So that's oxidative cleavage. You don't need to know the mechanism. You just need to know what happens. And then the other, it's still an oxidation reaction, but the other thing we talked about was you can add a syn-diol, so two wedges, two alcohols right next to each other, and you can use osmium oxide or cold KMNO4. KMNO4 ends up being like a jack of all trades. It comes up a lot, and it is a really good oxidizing agent. So this is all you need to know about adding oxygens to double bonds. You need to know that O3 will cleave the double bond. You need to know that if there's a hydrogen initially on the double bond and you want an aldehyde, you use O3. KMNO4 actually works in either of these situations. The only thing that it does differently than O3 is if there's a hydrogen, it keeps oxidizing it, so it's not really that useful. So at this stage, you don't know how to use that well, so I would focus on just using O3. And then osmium oxide are cold, KMNO4 adds syn-diol alcohols. So I hope that answers your question. Any other questions y'all have for me? If R double bond R plus O3, yes, exactly. That's what you need to know. Any kind of R groups, double bonded, it will cleave and turn into, so say this is R1, R2, R3, R4, it'll turn into R1, R2 plus R3, R4, and these are unchanged. And KMNO4 does basically, in the presence of O3, sometimes there will be a solvent. So like if you see something like this, it's a solvent. KMNO4 will actually do the same thing if it's hot. But if one of these R's is a hydrogen, then things get dicey. So if one of those R's is a hydrogen and you want an aldehyde, you just use O3. That's a good question. Any other questions? In 2 minutes, I am going to have to take a cake out of the oven. So just a fair warning about the timer that's about to go off. Anything else y'all want me to review? I did post the video key for test 2 last night. So if you hadn't had a chance to look over that, I mentioned I'd gotten for some reason mixed up on this question 16 when I read it in class. I think I didn't read the whole question, but it asked which of the following is not true of enantiomers. So enantiomers do have the same boiling point and melting point because they have the same intermolecular forces. And then they also have the same density because they have the same mass. So that narrowed it down basically to C or D. And enantiomers have different reactivity towards chiral reagents, but they act the same if the reagent is achiral. So that's not true. So the answer was specific rotation, but I think I got mixed up because I was thinking, oh, they have the same specific rotation. It's just in opposite directions. But the answer choice doesn't say that. So that's why I think that was the answer that I went with. Okay, somebody asked about R versus S. So I'm wondering if there's a specific situation where it's confusing, like a specific representation, like Fisher, or sometimes I think these 3D ones can be really confusing, where you like fill this in and there's a thing pointing straight down. But basically, you're just trying to determine R versus S helps you determine essentially if it's like left or right-handed, right? Because these mirror images seem like they're the same molecule, but they're not. They're non-superimposable mirror images, just like your hands. So your hands look like they're the same thing, but if you try to actually put them on top of each other, you can't. If you have to flip it over, but this now doesn't look the same as this anymore. So that's what RNS tells us. Is it sort of like the left hand or the right hand? And there's not one that goes with one or the other. It's just sort of a version that we have for naming that. So we assign priority based on Kahn-Ingold prelog, which is about mass of the thing directly attached. So here I think bromine. Oh, I'll be right back. Okay, I'm back. In 5 minutes, I'm going to have to move him to the cooling rack. Yeah, I'm making a strawberry cake. That's what my nephew requested. Pretty cute. He's going to come over and help me decorate it today. I love it. Okay, so let's see. So yeah, you do based on the Kahn-Ingold pre-log, which is the molecular mass of the thing directly attached. So bromine is 1, alcohol is 2, and then CH3, the carbon right here, would be 3. But you have to make sure that the lowest priority, in this case it's hydrogen, is pointing away from you. So like for me, I would float up above is how I would picture this. So that would be easier for me to visualize. Then the CH3 chain would be here, the OH would be here, and the bromine would be pointing down. And then I would just 1, 2, 3, and that's going to the left, and the hydrogen's pointing away from us, so that's S. But specifically for Fischer, yes, that's a good question. If you have a Fischer like CH3 and Cl, OH, and then here we had, I think I maybe know the one you're talking about, and it's CH2OH or something. This is not a chiral center, so this is, you can't assign R or S. So that, I think, is the question you're asking. Question 2 on the review sheet. Where's my iPad? I think I have that pulled up already, possibly. So I think one of them is actually not a chiral center. Let me see if I can pull it up. Maybe. Here we go. Okay, yes. Are you asking about this one? I think you might be. Question 2 on the review sheet, the first one, the bottom. Okay, so yes. So this is, it's like CH2OH, OH, H, 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 and CH3. So for this one, the first thing I'm going to say is if there's two things that are directly attached, then that are the same, then it's not a chiral center. You have to have 4 different things to be a chiral center. So this is not a chiral center. This one is. So 1, 2, 3. So this would be R. And then the hydrogen's pointing away from us, so it's actually, or towards us, so it's actually S. So this only has 1 chiral center. So I would name this 1, 2, 3, 4. This is butane, and it's a diol. There's 1, 2. So I would name this S, butane. It'd be butane, 1, 2 diol. So there's only 1 chiral center on this. Yes. Okay, so I would not include this part in the answer. When I said assign R and S configuration, 1, I think I just put S, and then 2 is either RR or SS, I don't remember. But all the rest of them had 2 chiral centers, and then the number 1 only had 1 chiral center. So yes, that one's not a chiral center because they're even. Okay, I think I answered that one. Oh, yes. Yep. Okay, great. What other questions do you have? Or does anyone have? Nope. Well, actually, my timer's up to go take the cakes and put them in the... Actually, they could probably go a little bit longer. Anything else that y'all want to cover? A big one that a lot of people got wrong was for E2 reactions. So at the very end of class yesterday, we were talking about nucleophile, or trying to tell the difference between SN1 and SN2. So if a nucleophile is strong, it'll favor 2. And if it's weak, it favors 1. And that's because of the nature of those mechanisms. And then when you break that down even further, primary, secondary favors SN2. Secondary, tertiary favors E2, heat, and a bulky nucleophile also favor E2. But for E2, you need to make sure that you check for stereochem so that it's anti-periplanar. Like if it's in a ring, they both need to be axial. If it's in an open chain, you need to use a Newman projection. And always check for Zaitsev versus Hoffman. If it's bulky, it'll go Hoffman. If it's small, it'll go Zaitsev. And then over here, they both are favored by secondary, tertiary. So really the only determining factor is bulkiness and heat. And then also always make sure you check for Zaitsev on this one. Zaitsev versus Hoffman. And on both of these, SN1 and E1, you always check for rearrangement. Okay, Chelsea asked, can you go over stereoisomers? Yeah, so I also have a similar tree for isomers. So I sort of break down isomers as constitutional. Constitutional isomers have the same number of carbons, hydrogens, and whatever else is on them. Like if you had a bromine here and a bromine here. They have the same number of everything that's attached to them, but they're not arranged in the same order. So like these don't have the same condensed formula. So I think there was a question, I think it was on here actually, maybe, or maybe it was something else I did. It was this one, question 6, where these are, these are not isomers because they don't even have the same number of chlorines, and you have to have the same number of everything to be isomers at all. So like these aren't isomers, these are not isomeric. But if they have the same number of all the atoms, of each individual atoms, then that's what an isomer in general is. So you have the constitutional and then stereoisomers. And stereoisomers are anything that has the same condensed formula. Like if you were to just write out the condensed formula, it's constructed exactly the same, but there's like a 3D component that you have to consider. So when I think of the 3D component, I think of that in 2 categories, and one is enantiomers, which are mirror images that are not superimposable, and the other is diastereomers. And I say diastereomers are diastereomers. I don't know if I spelled that right. Is everything else. So diastereomers consists of cis-trans. If you have like this versus this, these are the same condensed formula, but they're arranged differently in space. And also if you have RR and RS, if there's multiple chiral centers, they're not mirror images. Everything that's attached to them is the same. And so they must be diastereomers. And sort of as a follow-up to that, David said, I'm having problems differentiating. Oh, hang on. Before I answer your question, I'm going to take my cakes out of the thing and put them on a cooling rack. I'll be right back. Okay, I'm back. Thanks for your patience. Okay, so David asked the difference between constitutional isomers, meso compounds, identical, and not isomers. Okay, that's a good question. So I'm going to redraw my isomer tree over here. Isomers in general have to have the same number of all the atoms attached. So these are not isomers because I always write them out. So these molecules consist of chlorine, carbon, hydrogen, chlorine, and bromine. And I just do one in the column on the left and one in the column on the right. So these have 1, 2 carbon. This one also has 2 carbons. So they have the same number of carbons. Hydrogens, this one has 1, 2, 3 hydrogens on the left. This one only has 2 hydrogens. So that right there tells me these are not isomers. because if they were isomers, everything would match up. So in this example right here, there's 6 carbons on the chain. It's made up of carbons, hydrogens, and bromines. There's 6 carbons on the ring for both of these. And then there's 2 bromines for each one. That's easy. So I'm going to write that out first because you can see them well. And then I'm going to count up my hydrogens. So there's 2, 4, 6, 7, 9, 10 hydrogens. And then over here, same thing, 2, 4, 6, 7, 9, 10 hydrogens. So these have the same number of carbons, hydrogens, and bromines. So these are definitely isomers. But they don't have a different condensed formula or name. If you were just to write out the name of this, I'm looking at this and they seem to be arranged the same. So this looks like it's cyclohexane. And you have 1,2-dibromo. So this is 1,2-dibromo cyclohexane. And that is a correct name for both of these, but it doesn't differentiate between the two, and they're not exactly arranged differently in space, right? One of them has 2 wedges, and the other one has a wedge and a dash. So they're not exactly the same. So if they have the same base name, but they're not actually the same molecule, that's the same as like these are both called hands, but they're not the same hand. One's left and one's right. Or if you have 2 gloves, they're both gloves, but they're not the same glove. One's left and one's right. So this would be a type of stereoisomer, and we haven't determined what kind yet, but we sort of went down our decision tree. So we saw that it was an isomer because it has the same number of carbons, hydrogens, and bromines. It's not a constitutional isomer because its name would be the same. Constitutional isomer would be if you had, for example, let's see, 1, 2, 3, 4, 5, 6 with 2 bromines. I think this would be a constitutional isomer. So there's 6 carbons here. There'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens and 2 bromines. So this is a constitutional isomer pair because, sorry, I'm going off camera. It has the same number of carbons, hydrogens, and everything as these two. So these are constitutional isomer pairs. But this is not a constitutional isomer of each other because it's arranged exactly the same way. It's a cyclohexane with 2 bromines on the 1 and 3 position. So this must be a stereoisomer, if you can compare these two together. And then we have to go one step further on the stereoisomer pair and decide if they're enantiomers, which means non-superimposable mirror image, or diastereomers. And when I look at this, it does not look like the mirror image because this has 2 wedges and this has a wedge and a dash. So when I see that it's not a mirror image, then it must be a diastereomer. Diastereomer is everything else, right? Not a mirror image. Enantiomers are specifically non-superimposable mirror images. So that's the difference between constitutional isomer pair would be these two, where they're totally constructed differently. Stereoisomer would be here. So they're constructed in a way that is similar, but the 3D arrangement in space is different. And then you have to decide if it's an enantiomer or if it's a diastereomer. And then mesocompounds are actually something different. So mesocompounds are actually not isomers. Oh, this is dying. Let me grab a charger here. Meso compounds are actually not isomers because they have a plane of symmetry through the middle of them that makes it to where even though they have chiral centers, they're not isomers. So they're just like a unique case. They're very different than anything else because normally if something was not isomeric, it wouldn't have a chiral center on there. But meso compounds have 2 chiral centers at least. But even though it has 2 chiral centers, the mirror image of it is identical and it is superimposable. So because there's a plane of symmetry through the middle, it actually, even though it has 2 chiral centers, it actually is a meso compound. So this actually is a meso compound because if you took the mirror image of this, there's a plane of symmetry right down the middle. So this is a chiral center and this is a chiral center. There's no question about that. But if you took the mirror image, you would get 2 dashes. And if you have 2 things pointing, well, we'll say these 2 bromines pointing away. And if you flip it over, those 2 bromines will be pointing towards you. So they're actually identical. So the relationship between these two, these are meso compounds. So they're not isomers, they're identical. So I hope that kind of clears it up. I feel like that's kind of a lot to go over, but overall, that's kind of the basics of it. And I think practicing, especially on Fisher projections, will help, but that is going to come up on your final today. Okay, and then Sydney asked if I could do a summary for knowing what's SP2 or SP3. Yeah, okay. I'll use actually this, something similar to the one that was given to me today as a nomenclature. Okay, so what I look for is the number of sigma bonds around each thing. So right here, there's 4 implied hydrogens, or 3 implied hydrogens, 4 bonds to carbon. That's 4 sigma bonds. So I count up the number of sigma bonds. There's 4. So that must mean it's S and 3 P's. So if there's 4 sigma bonds, it's sp3. This carbocation, there's no implied hydrogen because of the formal charge. You need to know that. It starts with 4 minus 3 equals plus 1. So there's not an implied hydrogen there. So there's only 1, 2, 3 sigma bonds. So that must mean there's 1 S and 2 P's. So sp2. Right here on this double bond, there's 1 hydrogen that's implied, but then the rest of them are there. But this is a pi bond, not a sigma bond. There's only 1 sigma bond present in the double. So there's only 1, 2, 3 sigma bonds. So spp, so that must be sp2. So the biggest thing is if you can just count up the number of sigma bonds, you'll be able to figure it out. On this carbon-carbon triple bond, there's only 1 sigma bond in the middle of those 2, and then the sigma bond on the other side. So there's only 2 sigma bonds, so sp, so it must be sp hybridized. So I literally, that's funny. So I literally just go through and count up the sigma bonds, which that's different than formal charge. In the formal charge, you count up every bond. So make sure that you're not getting them mixed up. But for sp hybridization specifically, I count up the sigma bonds, and that's it. The other thing people will sometimes do is just like the number of electron groups that are attached, like 1, 2, 3 electron domains, and that helps too. But if that's confusing to you, don't do it. That's confusing to me, so I don't do it. Okay. Any other questions? Mechanism for HBr. mechanism for adding HBr is very similar to the mechanism for adding acid catalyzed water. So you just break that apart. Always the alkene attacks the electrophilic portion first. So the hydrogen adds and you get a carbocation here, and then the bromine will attack. And that's how you get the addition of HBr across a double bond. Oh, went off camera there. So, and most of our additional reactions follow something very similar. Sydney asks, is knowing the different rearrangement shifts important? There's only 2 rearrangement shifts. I would know them just so that you know what to expect. Basically, you need to know here there's a hydrogen, here there's not a hydrogen. So if this were to undergo rearrangement, a methyl would shift because there's not a hydrogen. And if this were to undergo rearrangement, a hydrogen would shift because that'd be easier, and it would look like this. So that's kind of the extent that you need to know about rearrangements, is just if it can trade places with something to become more stable. Like if there's a methyl group on this, the HBr mechanism, it would attack the H, and you'd get Br minus, because that would happen. And you would have a carbocation add right here, because the double bond is what gets broken. So hydrogen adds on this side, and then this is missing its bond. That goes away. So there is a hydrogen here that can trade places, and this carbocation would be more stable. So rearrangement would happen there, and then the bromine would attack. I hope that answers your question, and I also hope it answers Chelsea's at the same time. And then I think that is Penguin William. So asked about question 9 on the review. 6, 7. Here we go. Question 9 on the review. This is a multi-step reaction. Have I used up all my pages? I just cleared off my Rocketbook yesterday, and I have used up all the pages. That's a real bummer. Let me see if I can't just find one that I can use that's pretty clear. Nice. Okay. So this is a multi-step reaction. Part 1 is bromine and light. So I'm going to ask you what kind of reaction you think that could be. So if I was working this and I had Br and light, I would ask myself, what kind of reaction could this be? And yes, I think it's a radical reaction. We've only learned a few, acid base, and there's nothing like that you can see. There's substitution or elimination. There's not a good leaving group on here, so it's not that. And then addition reactions, well, there's not a double bond to add to, so it can't be that. And you would need a good solvent for this to add on, and not a radical initiator. So the last one it could possibly be is a radical reaction, and HNu is a radical initiator. So if you expose bromine to light, that should be bigger too, it will heterolytically cleave to give you 2 bromine radicals. And then it will steal a hydrogen. And in the case of bromine, it will steal the most stable hydrogen, or this hydrogen that will give the most stable radical. And radical stabilities follow that of carbocation stabilities. So I'm going to change this a little. So a tertiary radical is better than a secondary radical, is better than a primary. And if you could add resonance, that's even better. There's no resonance here, but this could generate a tertiary radical. So this bromine is going to steal one of the electrons from that. It's going to steal the hydrogen and one of its electrons and leave a radical behind here. This will make HBr, and then you still have this radical it didn't do anything from before. So that's the first step is initiation. This step is propagation. And then this will come and attack. And this is termination because the radical attaches. So you get this bromine. So that's step 1. And then we combine this with MEO, and it's MEONA, but I automatically make that MEO minus, MEOH, and heat. So what kind of reaction do you think that is? If there's MEO minus, MEOH, and heat. I always go through my list of reactions up here. Is it acid base? I don't think it's an acid base. Nice. I agree with y'all that it's an E2. Is it substitution elimination? It looks like it could be that because it has a good leaving group. I don't know why I put a check on acid base. It has a good leaving group and it has a nucleophile. So I agree that it would be a substitution or elimination because it's a strong nucleophile, because it's negatively charged. It's going to go to the 2 side. And for 2 reasons, because it's tertiary and because there's heat, it's definitely going to favor E2 over SN2. Strong and clunky. That's right. Okay, so that's going to go to E2. Now, normally with E2, we have to check for stereochem, but guess what? They didn't give us any stereochem in this problem. So yay, we don't have to do it. And the other thing you have to check for is Zaitsev versus Hoffman. Zaitsev gives you the most substituted. Hoffman gives you the less substituted. So to check for that, I look at for my beta carbons. There's basically just 2 because there's symmetry right here. So this one and that one are the same. So for me, it's actually easiest if I just look and see what products it can make. So this could come here, take this, and the leaving group leave. And I would get a double bond right in the middle. Or if it takes this one, the double bond would go there and the leaving group would leave. So between these 2, there's 1 hydrogen here and there's no hydrogen on this one. This one's tetrasubstituted. So this is definitely the most substituted, the most stable, and this is definitely Zaitsev, which is favored by the narrow nucleophile. So this would be my answer, which is answer choice C. So William, you said you didn't know how to do it, but I think you did know how to do it because you answered all those questions. You just had to believe in yourself. The problem wasn't your ability, it was your confidence. Okay, so Macy asked, how do we know if it's supposed to have stereochemistry or not? Well, if they give you wedges or dashes, that's how you know. So in this case, the initial one was given to us like this. And then a radical reaction happened. So I guess technically we sort of do know that you'd get a mixture of bromines, that one's a wedge and one's a dash. But this is kind of a weird thing because it's a ring. So you'd also have to have a dash over there. So when it's something that stereochemistry doesn't really lend itself to, then I feel like they won't include it and then you don't have to worry about it. So if it doesn't start with stereochemistry and none of these answer choices have stereochemistry, I guess the E2 thing would, but it doesn't start with stereochemistry, so you can't know if it's in the plane of the page or not. So that's how I know. If it doesn't start with stereochemistry, I usually just don't worry about it. Okay, and then Sydney said number 4 from the chapter 10 homework. Oh boy, I don't have that handy. Let me see if I can pull it up real quick. I haven't looked at the chapter 10 homework in a hot minute. Chapter 10, I'm going to have to look at it because I'm grading it today. Let's see, chapter 10 homework. You said number 4, is that correct? Number 4, yes. Which of the following gas-phase reactions is a chain terminating step? Okay, so the steps of a radical reaction are initiation, and that generates radicals. So it generates radicals from nothing. So if you have like chlorine and you add heat to it or light, and a radical is generated from no radical before, that would be considered an initiation step. Propagation is anything that keeps radicals going. So this chlorine bumping into HCl would take one of these and it would become HCl, and then you'd also get a new chlorine radical. So that is propagation. And then termination is anything where 2 radicals find each other. So normally, like in our question above, we had a radical on our ring and a radical bromine, and they find each other, and that makes a bromine bond. So that's kind of the basic answer to your question, is that's what I'm looking for. And the question, I don't think I can share my screen, but I can say the question asks, what is a chain terminating step in, I don't have anything to wipe this off with handy, but the chain terminating step in the chlorination of methane, any chain terminating step in the light initiated chlorination of methane. So chlorine splitting up like this, that is an initiation step. That's answer choice A. So that can't be right because that's initiation. B looks like a propagation step to me because a chlorine plus CH4 results in a CH3 radical plus, what does it result in? A CH3 radical plus HCl. So basically this radical took a hydrogen, so it's keeping a radical going. So because of that, my computer's done. So because of that, I would say this is a propagation step. And then step C, this isn't the chain terminating step that we're used to seeing. Normally, we would see this CH3 find a chlorine radical, and they would react and terminate and make CH3Cl. But what C has instead is two CH3 radicals finding each other and making CH3CH3. And that is still a legitimate option for a chain terminating step. It's just not the one we want. We'd rather get something chlorinated. And then D looks like another propagation step because it has a CH3 radical plus chlorine making a new chlorine radical and CH3Cl. So this is kind of what I was talking about of like, oh, there can be a lot of side products that come as a result. Yeah, it was asking which of these options has two radicals combining that is a realistic possibility in a methyl termination. So if it had like CH3, CH2, CH2, CH3, well, I guess it'd be CH2 radical like this, it would be very hard for a methane to end up connecting this many times. I guess it's possible, but unlikely. So you did need to know that like it is reasonable for CH3, to combine with, to be formed, two CH3 radicals to be formed and combined. But basically, yes, which of these options has two radicals combining is what it was asking. Macy asked, will you explain what the determining steps are for the major reaction types? I'm not sure what you mean by that. Do you mean rate determining steps? Or just how do I determine what is going to be? Clarification needed. Rate determining. You don't really need to know the rate determining step for most of these. The biggest one is for SN1, SN2, E1, and E2. I'll try to fit it in on this page since I'm out of space. So SN1 and E1, I'll ask, what's the first thing that happens? Hopefully you know. The leaving group leaves and it forms a carbocation. So that's a difficult energetic step to achieve. So that's the rate determining step. And that's also why the rate is dependent only on the substrate with the leaving group on it, because that determines the step. In SN2 and E2, there's actually only one step, which is the nucleophile coming in and attacking the leaving group. So because there's only one step, that is the rate determining step. And that one involves the substrate and the nucleophile. And then the other thing is, yeah, for all the rest of them, if a carbocation forms, that's probably going to be the rate determining step, but I'm unlikely to ask questions about that. Or like the bromonium ion, the bridge ion forming is a high energetic step. A radical forming is a high energetic step. So basically anything that's not favored would be the rate determining step. But the biggest things that we really like hammer down on it for is for SN1 and SN2. So you can understand how concentration and the nature of the nucleophile and the substrate both can affect the rate of the reaction. Please correct me if I'm wrong. I've been going off of anything 2 has 2, things multiplied, anything one has one thing multiplied. That's correct. So like if you double the concentration of the substrate, then this would double. If you double the concentrate of the substrate and the nucleophile, it doesn't matter what happens to the nucleophile. The rate's only dependent on substrate, so it would still double. If you cut this in half, it would be if you cut both of them in half, then the substrate would be divided by 2. So that's correct. And then also, yes, SN2 is nucleophile times substrate, because SN2 literally means substitution. The N is for nucleophilic. And the 2 is two things are involved in the rate law. So SN2 involves both the nucleophile and the substrate. That's why it's SN2. SN1 involves only this the substrate. It only involves one thing, and that's why it's called 1. So that's correct. That's a good way to think about it. Okay, it's 9:50. We have about 10 more minutes. Are there any other questions that you want to ask? If not, that's fine. We can just wrap up early. Okay. Well, there's one. Came in. I am going to go get a rag to clean this off with because I don't have any more paper. Okay, so poison catalysts are funny. What I like about poison catalysts is that my students last year decided they were like sabotaged catalysts. But so in general, if you have H2 and a metal and you start with an alkene, only one thing could happen, which is, oh, I did not dry this well enough. I love Rocket Books because I love that I don't ever have to buy more paper, but it is so annoying to clean them off. Okay, so normally if you have an alkene and you have H2 and any kind of metal, platinum, palladium, nickel, whatever, there's only one thing that can happen, and that's that double bond goes away. If you have a triple bond in the same conditions, usually the same thing will happen is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Is that will go away. And I kind of liken the analogy to a stair step. Is you have an alkyne, and then it's exposed to a catalyst, and it rapidly goes from an alkyne to an alkene to an alkane. If you're going down the stairs, you don't stop for any reason, right? You're just like, there's usually not a good reason that you're just going to freeze halfway down the stairs. And the same thing is true if you have H2 with platinum, palladium, and nickel. There's no good reason to stop just in the middle of a stairwell. If you're stopping in the middle of a stairwell, it's because you forgot something or something bad is happening for the most part. So if you do stop here, it's because something bad has happened. Or it's like the situation has been sabotaged. Maybe there's like a fake stair there and you get your leg caught. Like in Harry Potter, there's a vanishing stair step. You can get your leg caught. So my students called this the sabotage catalyst. If you want to stop at an alkene from an alkyne, you can use H2 with Lindlar's catalyst or P2. One of them is also uses quinoline. So basically, if you see H2 and anything other than just plain metal, that means that the reaction has been tampered with or sabotaged, and there's going to be something that stops it at an alkene. And for all of these, it actually stops at a transalkene. Because the hydrogens add to the same side, they add syn, so you get a a cis alkene. Did I say trans? All these go to cis. Because the hydrogens add to the same side, so you get a syn addition, so you get a cis alkene. If you have a dissolving metal reduction, which I think is just NH3 and lithium, so literally the ammonium dissolves the metal, it will also do a poison catalyst, but this is the only way you can get a trans double bond to form with a poison catalyst. So basically, just be on the lookout for these and know that these will go all the way to alkane, but if it's been tampered with, it'll stop at if H2 and something else, it'll stop at cis. And if you just see, I think it's just, let me look real quick to make sure. I think the dissolving metal reduction reagents are just lithium and NH3, but I might be forgetting one. It is, yep, it's either sodium or lithium and NH3, and that's how you get your trans alkene. Okay, so that's the poison catalyst, is it just basically stops at an alkene. That was Angel. Any general rules to help us write our way through the exam? I wonder if you mean work our way through the exam. Yeah, so if I was going through the exam, if I were you, I would go through and find the easiest ones that you feel pretty confident about and do those first. Like, this is a final exam that's cumulative, so there are questions like, what's the formal charge on this atom? And you should be able to do that pretty quickly. And there's also questions like, is this R or S configuration? Things like that you've done a lot of, that you should be able to do pretty quickly. So if I were you, I would go through and do those first. If you start to get freaked out, calm down and tell yourself, like, it's not a big deal. My grade is pretty much probably only going to get better from here unless I totally bomb this. And then flip to the back and start going from the back and working your way forward. That helps me calm down because I get pretty bad test anxiety. And you can tell yourself, like, your goal is just to show me how much you've learned, and you have learned a ton. Like, you wouldn't even be able to ask these questions when you started this class. You learned so much about OChem now compared to when you started. So your goal should be to show me that and not to worry about what you're getting wrong. I think that will help you. The other thing is, let's see. So after you work your way through the easiest ones, go back through and do the ones that you're like, I'm pretty sure I know how to do these, and just like work up to the point that you can. And you may find that you know how to do a lot more than you think you do. Anyone that you get to and you're like, I just really have no idea, put a star by that one and leave it for the last pass through. And when I do the last pass through, that's when I start working on eliminating wrong answers, just to make sure that I narrow it down to like a 50-50 chance, or a 1 in 3 chance is better than a 1 in 4 or a 1 in 5. Also, if you have time to go back and check yourself, I don't change answers unless I can really convince myself that my new answer is right. And I work the problem out multiple times and I'm like, yeah, I definitely made a mistake here, and this is the mistake I made. That's when I'll change my answer. The other thing I do is, if I have time, you've seen me do this actually on like working through practice problems and stuff, is I answer why all the other ones are wrong, like why A, B, C, D, E. If A is the right answer, then I go through and I'm like, B is wrong because this, C is wrong because this, D is wrong because this, and E is wrong because of this. And that helps me if there's a more than one of these is correct, that I don't miss it. And it also helps me if it helps me convince myself that I got the right answer, or if there's like one I'm not sure about, it helps me with that. And I just thought of one more, but I don't remember what it was. So those are my biggest ones. The other thing, I wouldn't worry about. Okay, so I'll answer William's question and then I'll answer Margaret. So, William, I wouldn't worry about solvent. Solvent effects are like one of the least important things. Students can kind of get caught up in them, but usually you'll be able to answer the question based on the nucleophile and the substrate. Because honestly, usually in OChem practice problems, their solvents are bad anyway. So I wouldn't worry about that. I think you might be talking about DMS, maybe. Dimethyl sulfide is a polar protic solvent, but I wouldn't worry too much about the solvent. Okay, and then Margaret wants me to go over SN1 and E1, how they're done. So what's the first step of an SN1 reaction? And an E1 reaction? Y'all tell me, what's the first step? Oh, I just realized time's up, so I guess I'll just go over it quickly. Hopefully you know the first step of an SN1 and an E1 is, for both of them, the leaving group leaves and a carbocation is formed. If rearrangement is possible, it will undergo rearrangement. Rearrangement's not possible here, so it won't here. And if it's going to go to SN1, the nucleophile, so we'll give you a narrow, weak nucleophile here, will come and attack, and you'll get something like this. This is still positively charged, and then you'll have to go through a deprotonation step. And so SN1 is a substitution, a nucleophilic substitution, and it's one thing is involved in the rate. And then this, if it's an elimination, the arrows will be different. So if it's an elimination, it's stealing a hydrogen to make an alkene, right? Because it's eliminating stuff. So usually a bulkier one would be better for that. So it will come and take your hydrogen, and this will fill in, and you end up with a positively charged nucleophile, but usually you can add base to equal it out. So there you go. Okay, hopefully that's helpful to y'all. It's about 10 o'clock, so I'm going to sign off so that my commuters have time to get to class safely. And I'll see you in the class in 45-ish minutes. Yay, we're almost done. I'm so proud of you. Those of you who are taking OChem 2 next semester, I will probably still be doing these live office hours because I think they're fun and because I don't have a lot going on. And then I also, if you want tutoring, I also will be doing some tutoring. So I hope you all have a good morning, and I'll see you in the exam. Bye.